Hello and welcome students. Today we are going to start your class 12 chemistry, and the chapter that we are going to discuss today is group 16. We are going to talk about the general properties of the group 16 elements and about some of their compounds. So first of all, before we start talking about group 16, we need to know the members present in group 16 of the periodic table. Who are those? There is oxygen, there is sulfur, there is selenium, there is tellurium, and finally there is polonium. Okay, these are the members: oxygen, sulfur, selenium, tellurium, and polonium. However, the study of polonium is beyond the scope of our syllabus, so we don't need to talk about polonium here. We will talk about oxygen, sulfur, selenium, and tellurium so far. So now, first thing that we need to talk about this group is the general name given to this group. Okay, this group, sometimes it is called the oxygen family because oxygen is the very first member of this group. However, the name given to this group in general, that is chalcogen. Okay, chalcogens. Now, why are they called chalcogens? They are called chalcogens because the word chalcogen comes from a Greek word, and it means ore forming or ore producing elements. Okay, we see that in nature these elements like oxygen and sulfur, etc., they are found in ores. There can be many examples. For example, there is zinc blende. Okay, you must have heard of them in lower classes, zinc blende. Then there is iron ore. Okay, there is iron ore. These are, see, zinc blende is what? ZnS, zinc sulfide. It's a sulfide ore. Iron ore is what? Known as hematite. It is usually this. What is that? Ferric oxide. So basically they are sulfide or oxide ores. Okay, so since these elements are found usually in ores, they are known as the ore producing elements, which we know as chalcogens. That's why the name chalcogens is given. Okay, now apart from that, let us talk about the electronic configuration. Okay, electronic configuration. So I'm writing in short EC, electronic configuration. Okay, the first member, oxygen, it is very simple. You have done in lower classes, class 11, 1s2, 2s2, 2p4. For sulfur, it is 1s2, 2s2, 2p6, 3s2, and what? 3p4. For selenium, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, and 4p6. Okay, so as you can see, the general electronic configuration of the last shell or the outermost shell is what? In the first case it is 2s2, 2p4, 3s2, 3p4, 4s2, 4p4. Okay, so in that manner it will go on. We can say that the general electronic configuration is, for the last shell, for the outermost shell, is ns2, np4. And as it is ending in the p orbital, the electrons enter the p orbital of the outermost shell, that is the last shell is p orbital is the last to be filled here, so we are calling them p block elements, just like we talked about group 15 earlier. They are also p block elements, right? Now let us talk about some of their general properties. Now some properties we will not go into that much detail. For example, there is of course some things that you have already learned, like atomic size, ionic size, okay, electron affinity, electron negativity, etc. You have learned about those terms in class 11 and even lower in class 10, right? But there are some peculiarities that I need to mention here. Let's first mention the general thing, that is electron gain enthalpy. Electron gain enthalpy, in lower class you have studied this same term as electron affinity. The energy released when an electron is accepted or gained by an atom. Okay. So what happens here? They have a tendency, all of them have a tendency to gain electrons. Okay. However, as we know from our class 10 knowledge, electron affinity, what happens down the group, it decreases, right? If I write the members again, and I'm writing only till tellurium and not writing polonium right now, what happens is, as we go down the group, what will happen? Electron affinity, or now known as, here you can see written, electron gain enthalpy down the group decreases, right? That is the general trend that we have studied in class 10, is it not? But even in class 10, there is slightly mention of this, that oxygen, although it is the topmost in the group, it is not having the greatest electron gain enthalpy. That honor goes to sulfur. Okay, sulfur has the greatest electron gain enthalpy, and then it goes on decreasing as usual. Now why is that? Why sulfur is having more electron gain enthalpy than oxygen? This also has been talked about in lower classes, but I am just refreshing your memories. Oxygen is very, very small. Okay, as we know about atomic size, down the group the atomic size increases, right? And the first member is usually the smallest, and it is always, actually not usually but always, the smallest. Okay, so and it is so small that there is inter-electronic repulsion which prevents the incoming electron. Okay, which not prevents it, but rather there is a hesitation there. Okay, this is not present in sulfur. Sulfur being larger, it can accept electrons more easily. Oxygen being very small in size, it has little bit difficulty. That is one portion of it. Okay, then this is done, then we move on to the next thing which you have to know. Another very important thing actually is ionization enthalpy or ionization potential. Ionization enthalpy or ionization potential. Now you know that left to right, what happens? Left to right across a period, ionization potential increases. That you have learned in class 10, is it not? Ionization potential increases from left to right across a period. However, here we have an exception. That exception was not mentioned to you in class 10. So here you have to remember that. You have got a little bit of that in class 11. See, before group 16 comes group 15, right? But it, according to your old trend, what should have happened is group 16 should have more ionization enthalpy than group 15. However, it is not the case. Okay, so let us see this part. See nitrogen and we compare it to oxygen. This is group 15, this is group 16, right? So in group 15, what we have to do is, group 15, what we need to know is that group 15 it is coming before group 16. So the ionization enthalpy should be more here, but it is not so. Why is that not so? It is not so because of the electronic configuration. So if I write the electronic configuration of nitrogen, 1s2, 2s2, and what? 2p3. Okay, 2p3. And here what will it be? We have written just now 1s2, 2s2, 2p4. Now here, if I show the last shell, the outermost shell, 2s is completely filled and 2p is half filled. 2p orbital is half filled. Now in case of oxygen, what is there? If I show this, the 2s is completely filled, and the 2p is more than half filled. Okay, it is one more. So if it is half filled, it has extra stability. Because of that extra stability, we cannot remove the electrons from nitrogen as easily as we can remove it from oxygen. Same would be the case if I compare, say, phosphorus and sulfur. So let us talk about this ionization potential and the difference in group 15 and group 16. As we know, in general what happens? Ionization enthalpy increases from left to right across a period. However, the exception here is that group 15 and group 16 comes after 15 to the right side of 15. However, it has less ionization enthalpy. Okay, it has less ionization enthalpy. Why so? Because the electronic configuration is responsible for that. You can see I have written here the electronic configuration of nitrogen and the electronic configuration of oxygen. If you see this, the electronic configuration of nitrogen is 1s2, 2s2, 2p3. And that of oxygen is 1s2, 2s2, 2p4. Now, if I write the outermost shell in this format, you can see 2s is completely filled and 2p is half filled. Just like we can see now oxygen 1, 2s is completely filled, 2p is having 4, more than half filled. Now half filled electronic configuration gives extra stability to the group 15 elements, and hence it is more difficult to remove electrons from group 15 elements rather than group 16 elements. The same can be seen in case of sulfur and phosphorus. If I write sulfur and phosphorus here, nothing would much change here. If I compare here phosphorus and sulfur, this is phosphorus, this is sulfur. All I need to do is just change the 2 to 3. Still the same story. Still we have half filled and full filled. Half filled and not half filled, it's more than half filled configuration. So if it is half filled, it has extra stability, which makes it having higher ionization enthalpy than sulfur, which comes to its right. So this is the exception here that you need to remember, that group 16 elements, although they are to the right side of group 15 elements, they have lower ionization enthalpy than group 15 elements due to the half-filled configuration of the outermost orbitals of the group 15 elements, which gives them extra stability. Okay? Now let us talk about oxidation states. Okay, oxidation states. Now, if we are talking about oxidation states, we need to remember that oxygen, the first member of this group, oxygen can only show two oxidation state of 2. Other members can show far more larger oxidation states. Okay, they can show larger oxidation states. So if we talk about sulfur or selenium or tellurium, they can show greater oxidation states. Oxygen can show only oxidation state of 2. Why is that? That is also linked to the electronic configuration. As we see here, we are showing only the outermost shell. So if I am showing the outermost shell, see 2s is completely filled, 2p has two unpaired electrons in two orbitals, right? Two unpaired electrons, right? So it can show a valency of 2, divalent. However, sulfur, it is having 3s, 2 and 3p. Also we can see just like that 4, 2 are unpaired, right? So it can show the valency of 2 as well, but it can show oxidation state of, here we can see oxidation state of 2, we can see oxidation state of 2 here also, but we can see more oxidation states for sulfur which we cannot see for oxygen. Okay, similar case for selenium and tellurium also, but let us focus on sulfur and try to understand the oxidation states of sulfur. Sulfur, as we saw earlier, in the ground state it resembles exactly that of oxygen. However, in the first excited state, we can see this is the ground state. Okay, let me write. This is all for sulfur. This is the ground state in GS. In the first excited state, what will happen is the electron from 3p can jump to the vacant 3d orbital. Here we did not show the d orbital, right? But we know that there is possibility of having 3d. Is it not? 3d is there, but 2d is not there. Oxygen cannot show more than 2 oxidation state. Why? Because there is no possibility of having 2d orbital, but we can have 3d orbitals. 3d is completely empty, but in the excited state we can have one of the electrons jump from 3p to 3d, and in that case we will have 4 unpaired orbitals, 4 unpaired electrons in 4 orbitals, and thus we can say it will show oxidation state of 4. Now it can show even higher oxidation states. It can show even higher oxidation states. If I show the second excited oxidation state, so I will just reserve this one. Second excited state, then one electron from here will jump to one more. So as we can see here, there is 1, 2, 3, 4, 5, 6 unpaired electrons in 6 orbitals. So we can have an oxidation state of 6, okay, which is possible in case of sulfur but not in case of oxygen. Why not? Because oxygen does not have vacant d orbitals. It was the same case for nitrogen as well. If you remember in group 15, the first members of each group do not have vacant d orbitals, as a result of which this is not possible. Like this, they cannot show higher oxidation states. Okay.